Okay, let's look at number 2. Maybe we can just talk about number 2 and not have to write anything down here because most of the stuff is just right here on the page anyway. So it says, given the state space form, we have a Jordan block or Jordan form of the A matrix, and so these are really A or J. We could really just call this J, and B sub m and C sub m. And we're asked, is the system stable? Justify your answer. Is it controllable? Keep it completely controllable, completely observable. Justify your answers. So, first of all, we need to ask the question: is it a continuous time system or discrete time system? In either case, the answer is that the system is unstable. If we assume continuous time, we see that we have a positive eigenvalue. So, continuous time, the criterion is if there is a positive real part, system's unstable. So the system is unstable for continuous time. If we have discrete time, we look for the magnitude of the eigenvalue being bigger than 1, and they're all bigger than 1, and so it's definitely unstable for discrete time as well. So the system is unstable whether it's continuous or discrete time. Okay, so the first one is unstable, or no, it's not stable. Justify your answer. Well, the eigenvalues are either positive or bigger than 1. Positive and bigger than 1 in magnitude, so they're unstable. Part B, is the system completely controllable? Justify your answer. So we're going to look at the B matrix, B sub m matrix for the controllability question. And we're going to look at, well, first of all, for the distinct eigenvalues, are there any 0 rows? No. Okay, so these are not equal to 0. So that's good. So far, so good on the controllability side. Then we need to look at each of the Jordan blocks. See, -2 has 3 Jordan blocks. One 1 by 1, another 1 by 1, and a 2 by 2. And so when we have repeated eigenvalues, we look at the last rows associated with the Jordan blocks for the repeated eigenvalue. Okay, and so that would be, there is only 1 row for these two, so we look at these 2 rows for these first 2 Jordan blocks, and we look at the last row on the 2 by 2. And we need to have these be linearly independent. Okay, if they are linearly independent, then we have completely controllable. If not, then we don't. And we can see that the second one is just the first one multiplied by 2, so they are not linearly independent. No, not linearly independent, and so it's not completely controllable. Okay, so the answer for 2B is not completely controllable because the last rows associated with these 2 Jordan blocks in B sub m are not linearly independent. Okay, similar kind of thing for part C, completely observable. Again, the Jordan blocks go this way now in columns. So the first 2 are the associated with the -2 1 by 1 Jordan blocks. The next 2 are associated with the 2 by 2 Jordan block, and then the last 3 are the 3 distinct eigenvalues. So first of all, I guess we can look at the 3 distinct eigenvalue columns. They have to be not 0, and they are not 0, not equal to 0, not equal to 0. Those 3 are okay. And now for observability, we look at the first columns. First columns of C sub m for the Jordan blocks of the repeated eigenvalue. Okay, and so looking at these first columns, it doesn't matter that that there is one column that's all 0. That doesn't matter anymore. All we're looking at is, are these 3 columns linearly independent? And just looking at it, you can see this one has only 1 here, and so the other ones have some in the other 2 places, and so yes, it is linearly independent. Or you can do the determinant of this matrix real quick to prove that they're linearly independent if you can't see it. But I say yes, they are linearly independent. So that means it is completely observable. Okay, so That's that problem.